The central limit theorem is quite literally the bridge between probability and statistics, yet it remains one of the most misunderstood and misapplied theorems in all of quantitative finance. Well, no longer. In this video, we're going to cover everything that you need to know about the central limit theorem from theory all the way to practice. We'll start with this idea of a random variable, its accompanying statistics, extend this to a normal or Gaussian distribution, then we'll move on to a rough proof of the central limit theorem itself and talk about its implications. Once we're done with that, we will leave the classroom and apply it in the real world to stock returns and this idea of a trading signal. Very rarely do we have access to the population or data generating distribution for an event of interest. You can think of something like a stock return. Unlike my Jupyter Notebooks, which you always have access to, this Jupyter Notebook will be linked in the description below. I will also post it to the Quant Guild library on GitHub, where you can find all of my Jupyter Notebooks and associated YouTube videos, along with all of the source code for my Quant builds. At the top of this Jupyter Notebook, you'll notice some related Quant Guild videos applying probability and statistics to finance and trading, this idea of time series analysis, retail versus institutional trading, trading versus investing, this idea of accumulating edge over a series of trades or time, quant versus discretionary trading, and of course, busting 3 popular trading myths that these trading gurus love to propagate. If you're unfamiliar with any of these ideas, I highly recommend that you check these videos out first before tackling one like this. Moreover, these videos certainly take a lot of effort to create, so if you'd like to help support the channel so I can continue to create videos just like this one, please like, comment, subscribe, share. It helps me out tremendously. It is always greatly appreciated, and if you'd like to master your quantitative skills, check out quantguild.com. Maybe you come from a background in business, economics, computer science, and aren't too sure where to get started on your quant journey. Maybe you're an aspiring quant or a working professional looking to sharpen your quantitative skills. In any case, Quant Guild is for you. We have over 90 quant lessons in math, probability, finance, an adaptive practice engine that scales with your skill level so you can progress to more and more difficult topics with gamified rank-based progress, interview questions with fully worked solutions, trading games, courses from A to Z in math, probability statistics, coding, and more on the way. And all that's included with Quant Guild membership. And you can get started right now for free. So if you'd like to help support the channel and master your quantitative skills, check out quantguild.com. Without further ado, let's get started by talking about this idea of a random variable, by talking about how they are defined and using one to model the number of trades on a particular instrument within 100 milliseconds. So first things first, a random variable is defining a set of possible outcomes with accompanying probabilities or likelihoods. They are fully specified by their probability mass or density function, cumulative distribution function, or even the characteristic function. There are a lot of different types of random variables, both discrete and continuous, but we're going to look at one in particular to model this idea of the number of trades executed on a particular instrument over the next 100 milliseconds. And that is going to be this Poisson random variable. The Poisson distribution is parameterized by lambda, and that represents the mean or average expected number of trades over the specified time interval of 100 milliseconds in this example. So what we have here is the probability mass function. It is a discrete random variable. So each outcome has an accompanying probability. The cumulative distribution function tells us the cumulative probability up to a particular point, that is a certain number of trades. And the characteristic function is effectively the Fourier transform of the mass function itself, which we all know is unique. So we can go freely back and forth between the characteristic function, the mass function. If we sum the mass function, we get the distribution function. If we difference, we get back the mass function. In any case, what are we actually observing down here? Well, we're observing the theoretical versus the empirical distribution of trades observed over the interval of 100 milliseconds. So what we're doing effectively is we are going to experience 100 milliseconds and then record the number of trades we see. Experience another 100, record the trades, so on and so forth. And that is how we construct this bar chart on the right, this histogram. And what we're observing here is this sample of data that we observe over the course of 25,000 milliseconds is converging to this population or data generating distribution. And that's because the data that we're observing on the right is drawn from this theoretical distribution. Now, it's very important to note, in practice, we don't get the theoretical data generating distribution. This is what we're trying to model. If we had the dynamics itself, we wouldn't need to develop a model in the first place. We are going to need to make assumptions, and we are going to use those assumptions to construct a model to aim at making informed decisions under uncertainty. That is our goal, never to predict a specific outcome. We will never be able to predict the number of trades over the next 100 milliseconds. We will never be able to predict a stock price or a stock return. That is not the purpose of modeling in this context. Importantly, the sample that we're dealing with, these blue bars on the right, for all intents and purposes are random variables. That is, if I was to resample from this population distribution with a different random seed, then what you're going to observe is an entirely different sample of data. Now, it's true, if I continue to sample from this population distribution, eventually it will converge to the theoretical mass function. But for this particular sample of 25,000 milliseconds, right, we're observing trades every 100 milliseconds, all the way up to a cumulative 25,000 milliseconds, we can see a completely different sample of data here. So the empirical distribution is effectively a random variable. Asymptotically, as we observe more and more samples, yeah, it'll converge to this theoretical distribution. But why is this important? Well, this brings us to the idea of a statistic. Whenever I observe a sample of data, I can always take the average, find the mean or expectation, but isn't the empirical distribution a random variable? What does that make the sample mean? That sample statistic? Well, effectively, it makes that sample mean value also random. This goes for every single population or data generating distribution that is either well defined, like we have here a Poisson distribution, or even in theory where we're looking at some sort of sample of data that we collected. That is, the empirical statistics are themselves random variables. It doesn't matter if we're dealing with a Poisson distribution, Bernoulli, binomial, geometric, even continuous, uniform, exponential, so on and so forth. All of the empirical statistics are going to be random variables. How is this different from the population distribution? Well, if I was to compute the theoretical mean of the Poisson distribution, I would get lambda. That is the average number of events over that particular time interval. And in this case, we said that the time interval is 100 milliseconds and the event is a trade. So we parameterized our Poisson distribution by an average of 4 trades over each interval of 100 milliseconds. But in reality, when we observe a sample of data, that is, we look at 100 milliseconds, record the number of trades, look at another 100 milliseconds, record the number of trades, that sample of data that I just recorded is a random variable, and so is the average that I compute. And that is exactly what I'm showing you in this animation. What I'm doing is I'm going to observe some data. Let's say I observe it for what? 25,000 milliseconds. I'm going to record all of those trades that I observed in each block of 100 milliseconds, and then I'll take the simple average. And after that iteration, I'll reset the list and do it again. And what do you see here? You see that the mean for each sample of data is going to be different. It is a random variable itself. And you can see here in the first sample of data, I have a mean of 4 trades. Then I have a mean of 3.4, 3.2, 4.2. And what you're observing here is it's kind of oscillating around this theoretical value. And we know with statistical certainty that if we had an infinitely large sample size, then yes, all of these bars would be flat. Effectively, the empirical distribution would converge to the theoretical distribution, and so would all of the statistics. Okay, but how do we know that for sure? Well, that is guaranteed by the law of large numbers. If we're drawing from the same population distribution, then empirical statistics and distributions are guaranteed to converge to their population or the data generating distribution. If we're drawing from the same population distribution, just as we were in both of these examples, this is the probability mass function, the Poisson random variable governing trades that we observe in the next 100 milliseconds. If we continue to draw from a fixed distribution, then empirical probabilities, statistics, and distributions are guaranteed to converge. And I have a nice animation of what this looks like for you here. Effectively, I have that empirical mass function on the left, and on the right, I have the sample mean. And this sample mean is tracking the theoretical mean as the sample size increases. If this goes to infinity, this will converge to 4, and this histogram will converge then to the theoretical probability mass function that we defined above. And again, this occurs with probabilistic statistical certainty. That is given to us by the law of large numbers. This isn't a course on probability theory. There's a difference between the strong and the weak law of large numbers, but I will digress for the sake of brevity so we can move on to this idea of calibrated and out of sample distributions. This nice idea of convergence does not apply in practice. What we're doing here is we're drawing from the same population Poisson distribution for every single sample that we realize in this empirical distribution and this empirical statistic, the empirical mean. But in reality, we don't get to observe the population or data generating distribution. And what this can lead to is a series of modeling decisions that actually are incorrectly informing the likelihood of different outcomes. What does this actually look like? So we can't observe what the theoretical distribution actually looks like. What I'm going to do is I'm going to do exactly the procedure that I outlined for you before. I'm going to take a look at the number of trades over 100 milliseconds. I'm going to do that for maybe 10,000 milliseconds, and I'll compute the average. Let's say I get 4. Okay, well, what I'll do is I'll calibrate a Poisson distribution to that value that I observe in the data. And what I'm then going to do is I'm going to use that theoretical distribution to attempt to inform the next 10,000 milliseconds of trades. And this gets into the idea of non-stationarity, uncertainty, and lack of convergence. What are we observing here? We're observing the population mean that I calibrated my model to as to be 4. But when I observe the next 10,000 milliseconds of data, the empirical mean that I get is 2. That's nowhere near 4. We are grossly overestimating the mean value of the distribution over this next 10,000 milliseconds. And this brings us to the canonical question of modeling. How do we evaluate our model's efficacy? Well, in reality, events are uncertain. They're not random variables. We are using these models to attempt to define probabilities and likelihoods for different states of the world. That is effectively our goal in modeling. This raises some very important questions. In this context, when it comes to trades over 100 milliseconds, we can ask, is a Poisson distribution and the accompanying assumptions, we have this idea of independence, so on and so forth, is that a reasonable model for trades over intervals of 100 milliseconds? It's a very important question. Is the distribution relatively stable, or is there severe time variance? If the distribution was stable, we would observe something like this, where after we calibrate our model, we see the empirical distribution tracks our calibrated model quite well. But in practice, we're going to likely observe something like this, where our calibrated model and the observed data out of sample are fundamentally different. This leads us to the next question. That is, should this time variance persist? Is there a reasonable way to model it? Can we introduce maybe the notion of a regime to better capture these dynamics in different states of the world? For example, maybe this empirical distribution better reflects a period of high volatility. So when we observe trades in a period of high volatility, it follows this distribution, and maybe in a period of low volatility, it follows this one. In any case, what I want you to observe is how the statistics are different. Regardless of if we're dealing with the population or the empirical distribution, you can observe that the statistics are different. And we're not going to have this idea of convergence. If I keep sampling from the data generating distribution and I keep recording samples, I will never see convergence to a mean like I do here. And that's because the data generating distribution is always going to keep changing over time. And that leaves us a very important question to answer. Is there a way to determine if the statistics that we are observing deviate significantly from a population statistic? In other words, what we're observing here is the empirical mean is what? Roughly 2? But the data generating distribution that we calibrated has a mean of 4. We don't get to observe this in practice. What is the probability of observing this empirical mean? That's a very important question. Well, if we're asking a question pertaining to probabilities, what do we need to know? We need to know the distribution of the sample mean. And that is the question that we have to answer. If these statistics themselves are random variables, what distribution do they follow? If we can get to that distribution, we can answer necessary questions like, what is the probability of observing an empirical mean of 2 if the true population distribution has a mean of 4? And then we can actually assess the efficacy of that calibrated model. That is what we are building towards. So we need to understand what distribution the sample mean, this sample statistic, follows, since it is in fact a random variable. I hope it doesn't give too much away, but now we're pivoting to talk about this idea of a normal or Gaussian random variable. This is a continuous random variable, which is different from a discrete random variable like a Poisson random variable. But in the context of what distribution does our sample mean follow, you might be able to guess what the central limit theorem is now going to imply. In any case, we will build up to it. So we have the probability density function, the cumulative distribution function, and the characteristic function here that is going to define our normal random variable. And what you'll observe is the same nice convergence properties that we had above in the discrete random variable example of our Poisson distribution. You can see that the empirical histogram, that is our empirical distribution, will converge thanks to the law of large numbers, along with all of the statistics and associated event probabilities. Now, why is this different from our Poisson example? Well, in our Poisson example, we literally got probabilities with associated events. So the probability of observing 6 trades in 100 milliseconds by this particular distribution is roughly 10%. That is what the probability mass function defines. Does the density function define probabilities? Well, no. Effectively, there are an infinite number of outcomes for this particular density function. Anytime we look at a specific value, we can draw a vertical line for the input and match it to an output. This is not a probability. This you can think of as a relative likelihood. If I compare, say, this vertical line here to this vertical line out in the tail, which one has a higher likelihood of observing points around it? Well, clearly this one in the middle, right? There's more mass underneath the density function. So when we look at the probability density function for a continuous random variable, we have to think of it in terms of a likelihood, a relative likelihood, not a probability. That is fundamentally different from what we observed above. How do we then get probabilities? Well, we need to ask questions about regions. If we integrate this density function, we can get probabilities. If I integrate from negative infinity all the way to 0, I will get 50%. The distribution is symmetric. If I wanted to find the probability of observing a draw less than 2, I would just integrate, or less than negative 2, I would integrate to negative 2, and it looks like it's roughly 2%. So that is how our normal distribution works. It is effectively parameterized by a mean and a variance. This will dictate the location, that is the center of the normal or Gaussian distribution, and the spread. You can see a couple of different normal distributions here. We have this purple distribution that's a special kind. It has a mean of 0 and a variance of 1. Then we have this yellow distribution with a different mean and variance, and this green one with another different mean and variance. And what you're going to observe here on this slider is the normal distribution with different parameterizations will have different likelihoods of observing, or different probabilities of observing, certain outcomes. So if I was to integrate up to, let's say, 1 for this green distribution here, it's far more likely to observe occurrences in this green distribution than it is for this orange distribution. Essentially what I'm saying is everything that I showed you here with the standard normal distribution, a mean of 0 and a variance of 1, will hold for every shape of the normal distribution. So regardless of its parameterization, regardless of its mean and variance, we can integrate to find probabilities. We can compute relative likelihoods. That is very useful, but this is no different from any other random variable we could just define and calibrate. We can do this for a Poisson distribution, just like we did above. We can find probabilities and relative likelihoods here. We can do this for a geometric random variable, a Bernoulli, a binomial, a uniform exponential. Why do we care about the normal or the Gaussian distribution? Well, this is quite literally our bridge between statistics and probabilities. In other words, the central limit theorem shows that the distribution of sample means is normal or Gaussian. We are not proxying the data generating distribution. In this case, we know for certain that the distribution that generates the value for the empirical sample mean that we observe, that is, for example, this red line here, or any of these pink bars, we know for certain come from a normal or Gaussian distribution. And that is a crazy result. Let's take a look at a rough outline of the proof and see exactly why this is the case. The full proof is certainly beyond the scope of this video. I would be happy to create one on this topic if there's interest. Just let me know in the comments below. In any case, I want to give you a rough idea of what this proof looks like using the characteristic function, so you know we're not just pulling this result out of thin air. Let's get to this rough proof. What I have here is the sample mean. This is actually the standardized sample mean. I'm subtracting out the population mean. I'm dividing by the standard deviation scaled by the square root of the sample size. And this is defined as z sub n. This is our standardized sample mean. What we're going to do is we're going to apply the characteristic function and this nice rule that leads us to using the sum of independent random variables as the product of their characteristic functions. And that is effectively what we're applying here. That's how we get to this step in the equation. We're then going to substitute in a Taylor series expansion, and we will get to now this step. If we apply the limit as the sample size approaches infinity, we get e to the negative t squared over 2. That is the characteristic function of this standardized sample mean. Okay, well, what do we know about characteristic functions? Well, they uniquely define our random variable. Where have we seen this before? Well, we looked at a normal or Gaussian characteristic function above when we defined it, and we see what? This is e to the I mu t minus 1/2 sigma squared t squared, but this is standardized. So the mean is 0 and the variance is 1, which means if I substitute those values in for mu and sigma, I will get 1 squared, which is just 1. So I'll remove sigma altogether. Then I plug in 0 for mu. That removes the first term. What am I left with? The characteristic function of a standard normal random variable is just e to the negative t squared over 2. That is exactly what we get there. So this is a rough proof of the central limit theorem. And this is actually going to hold by the Levy continuity theorem. Effectively, convergence of a characteristic function at t equals 0 implies distribution convergence. In other words, this sample mean is then going to converge to that standard normal distribution as n approaches infinity. And again, this is regardless of the population distribution. So what we've done here is we've just shown that the distribution of our standardized sample mean is going to be standard normal. If it wasn't standardized, we would just add the mean and scale by the standard deviation to get the appropriate variance. And that is an incredibly cool result. Let's take a look at an example of this in action. What I'm going to do is I'm going to look at the empirical Poisson means, and I'm going to plot it against a normal distribution. And what you're going to see here is as I continue to sample from the Poisson distribution, I take the average, I add it to the histogram. I'll do that a very large number of times. It's no coincidence. It's not by accident. You're seeing the histogram converge to a normal, a Gaussian distribution. That is ensured by the central limit theorem. This is given by a Poisson random variable. It could be Bernoulli, binomial. It doesn't matter what the population or data generating distribution is. All of these sample means will converge to this normal or Gaussian distribution. A key component of this result is that more samples lead to more confidence and eventually convergence to the population mean, which is exactly what the law of large numbers implies. So if we take a look here, what we're doing is we're computing the variance of the sample mean. So we know the sample mean is a random variable. We know it follows a normal distribution, but the variance is going to be dictated by the sample size. As the sample size increases, right, n is in the denominator. If we increase the denominator, then the overall quantity gets smaller. So as the sample size increases, what happens to variance? Well, variance starts to tighten up. And that's exactly what we see here in this animation. As n increases, the variance becomes tighter in that distribution. So effectively, what are we saying? Well, the more samples that we have, the more confident we are in the observed sample mean that it will be in fact closer to the population mean. And it doesn't stop there. Effectively, we've unlocked an entire suite of tools that we can apply to the statistics that we observe to assess something about the population or data generating distribution that we know is normal. And this goes back to our key questions. If statistics themselves are random variables, right, our sample mean is a random variable, what distribution do they follow? Well, the sample mean by the central limit theorem is going to follow a normal or Gaussian distribution. And what about the other key question? Is there a way to determine if the statistics we observe, that is, remember, they are a function of our specific sample, do these deviate significantly from a population statistic? So for example, we may be interested in returns. Is the sample mean return what? Greater than 0 or less than 0? We can now assess the probability of the data generating distribution having a mean of 0, or if there is a positive skew. That is effectively helping us bridge the gap between statistics and probabilities. I have now an example for you here where we don't have a theoretical or population data generating distribution. Instead, I'm observing stock returns, and I'm going to take the sample mean. We know that sample mean follows a normal distribution, and that's what I have on the right here. This yellow line, this yellow vertical line, represents what? The mean stock return. We can see that there is what? It's slightly positive, and this is going to be a normal distribution that we calibrate to that mean return. What I want you to notice here is what happens if I shift the distribution. Does the likelihood of observing the mean return increase or decrease as I shift the distribution to the right or left? Well, clearly, the likelihood of observing this mean return is maximized in the center, where there's the most mass available. This brings us back to what we talked about when we introduced the idea of a normal distribution, right? We're assessing relative likelihoods. In other words, we know for certain now that the population or data generating distribution for this sample mean that we observe is normal, which means what? The distribution that maximizes the likelihood of observing it is the one that has the sample mean return in the center. This is the idea of maximum likelihood estimation. We're maximizing the likelihood of observing this specific value, and that is how we can parameterize our normal distribution. Sure, there are other approaches, moment matching approaches, so on and so forth, but this is one way to go about generating now probabilities. Now I have a normal distribution. Effectively, we've already observed this mean return. We know the population distribution is normal. What distribution maximizes the likelihood of observing that mean value? Well, that's going to be the one that has a mean centered at the return that we've observed. And that's exactly what we see here. That is how we can then parameterize the normal distribution. And once we parameterize it, we can find probabilities. That's exactly what I showed you here. If we integrate, we can get the likelihood and probabilities of different states of the world. Now, there are some important considerations and limitations, right? When we model the population distribution, yes, we know it's normal, but we don't know the actual mean and variance of that distribution. It could be over here. It could be over here. It could be flatter. It could be sharper. We have no idea what that looks like still. All we're doing is assessing the likelihood of observing this sample mean value based on different population distributions. So clearly, if I shifted this purple distribution all the way out to maybe 20, right, the likelihood of observing this point here is 0, right? We're not going to really see that as an observation. So yeah, the distribution is most likely centered somewhere around here. But the catch here is that it's going to change over time. So if we apply the central limit theorem to something like a fixed distribution, like the Poisson distribution example here, it's going to converge. And this normal distribution is going to perfectly represent the distribution of sample means. All probabilities, statistics, so on and so forth will converge. But with something like stock returns, it's going to constantly change over time. And that is a key consideration here. We can apply the central limit theorem, and we're going to look at some examples on stock returns and a trading signal in a moment, but we can still apply the central limit theorem, but we're going to have to change the interpretation because there is a time variant nature to this distribution that generates the sample mean return. This is something that we didn't have when we had a fixed population distribution. All right. So with the central limit theorem, we do unlock a whole bunch of tools. Parameter calibration, we can go from statistics to probabilities. We can apply confidence intervals, hypothesis testing, so on and so forth. But as I said above, there are some important considerations when we now move on to the real world. So we understand the central limit theorem. We understand that random variables follow a normal or Gaussian distribution. We can bridge the gap between statistics and probabilities. Let's leave the classroom and apply this now to stock returns and a trading signal. What we're going to do here is we are going to observe sample mean returns of NVIDIA over disjoint 90-day blocks. So I'm going to observe 90 days, take the mean, that is going to be a return. I'm going to do this for another 90 days, another 90 days, so on and so forth. This is very similar to what I did at the start of this video, where I talked about recording the number of trades in 100 millisecond blocks. Now, I know that the distribution of sample means is going to be normal or Gaussian, or so I think. So what I'm going to do here is I am going to observe what? The NVIDIA stock returns, and I'll parameterize a normal distribution to maximize the likelihood of observing the block means. And what do I find? Well, if I compute the mean of the disjoint 90-day block sample means, I find what? That there is a mean return of 0.21% with a standard deviation of 0.049%. That means that the probability of observing an average return of less than 0 during these 90-day blocks is going to be approximately 0. And if I was to treat this as a geometric random variable, I could find the expected number of years required to observe a negative mean return given a period of 90 days. And it turns out if we apply the central limit theorem, we parameterize this normal distribution and compute this probability, it will take what? 42,290, roughly 6 years to observe just one negative return in this 90-day block, specifically a negative sample mean return in one of these 90-day blocks. All right. Well, that sounds pretty good. We should just dump our entire portfolio into NVIDIA, right? Well, not quite, because if I look back at the block mean returns, what actually happens? Well, I observe in all of these 74 blocks, 27% of them actually have negative mean returns. So 20 of the 74 have negative returns. And clearly we didn't wait what? We didn't wait 42,000 years. In fact, the years required to observe the negative blocks we've already experienced are what? This is, I can't even read, this is 845,915 years. Clearly, our model is severely underestimating the risk of observing a negative sample mean return. And why is this the case? Well, this brings us to the idea of the limitations and considerations associated with applying the central limit theorem in practice. In this case, we're looking at specifically stock returns, but this goes for any time variant data generating or population distribution. Again, we don't know what the parameterization of the population distribution is. If it's a sample mean, we know it's normal, but we don't know what the parameterization of it is. So what I've done here is I've calibrated by the central limit theorem my sample mean returns, and that is this orange dashed line. But what's going to happen in reality? Well, the data generating distribution, that sample mean, right? That sample mean that we're observing and parameterizing our fixed normal distribution with to assess the likelihood of different states of the world, right? That's not a good model because the data generating distribution is time variant. It is going to change over time. And as you can see, right, the likelihood of observing negative returns over here in reality is what? Very likely relative to the fixed distribution, which says it has a probability of roughly 0. That is the key point to understand when you apply the central limit theorem and even the law of large numbers in practice. There is no convergence. There's no statistical, probabilistic, or distribution convergence. Everything is time variant. Probabilities and likelihoods will change over time. Your capacity to model different dynamics under different regimes will certainly vary. That is how we can effectively understand the application of the central limit theorem in practice. It is good for a point in time, assuming relative stability. But after that, we're going to need to create a new model. We're going to develop new assumptions, reevaluate. That is effectively why we all still have a job. Our job as quants is to build models, make assumptions, update models, and update assumptions as things continue to change. If we do this effectively, we can accumulate positive expected value, we can accumulate P&L, and that is how we make money. So this is effectively why the central limit theorem is breaking down for us. How is this useful as a point in time snapshot? This is roughly what I had mentioned here, where this is a reasonable proxy maybe for this point in time, but as time marches on, right, it's definitely not going to be useful. How is it useful as a point in time proxy, maybe in the context of a trading signal? In some cases, the assumption that the sample reflects the data generating distribution is less violent than others. If I'm using a sample mean from 3 months ago to inform my normal distribution today, yeah, that's probably not useful. But if I'm trying to assess the likelihood of a specific observation at this point in time, then this can be very useful depending on the stability of the space. I have a very simple example for you here. Let's say I have a trading signal. I'm trading some sort of cross-sectional equity strategy. This is going to be a sentiment-based strategy. And I'm trying to assess the sentiment of an equity before 9:20 a.m. I only have 50 unique documents. So let's say I collected data from 8 a.m. to 9:20 a.m. I only have 50 documents. I calibrate a normal distribution and I want to assess the probability of drawing an incorrect signal value. This is essentially a confidence question, right? What is the likelihood of observing the sample mean that I've already observed? So if the probability is too low, I won't include it in my equity basket that I'm going to trade, right? I have some sort of quantile breakdown of my signal. I'm going to go long the equities in the top basket, short the equities in the bottom basket, and I have effectively this equity in my top basket. I have 50 documents suggesting that what? It is tradable. I want to go long, but what is the probability of observing that mean return if I only have 50 unique documents? Well, this has to do a lot with the confidence of observing that specific sample mean value. We know that the central limit theorem is going to increase in confidence as the sample size increases. Here, we don't have a large enough sample size, so what we can do is we can ask an interesting question. What is the probability of observing the value that we've already seen or greater given some sort of conservative distribution? I don't know what the population or data generating distribution looks like. It could be very flat. It could be shifted in this direction. It could be shifted in this direction. I'm going to pick a distribution that I'm satisfied with and assess the probability of observing that specific mean sentiment value or greater. How do I do that? Well, I take my null sampling distribution, I find the point of interest, and I integrate past that point, and I integrate up to infinity, and I find what? That the probability of observing that specific sentiment mean value is very, very small. It's less than 1%. 8%. Am I going to now trade this in my long leg of my portfolio? Absolutely not. Given I'm abiding by this null sampling distribution, the likelihood of observing this value is far too low. I'm not confident that the sentiment is effectively positive. So what I will do is I will exclude it from my basket, or I will abide by some specific rule set, and then I will trade the remaining assets, assuming they have a reasonable degree of confidence in each bucket. The point here is it doesn't matter that the distribution is changing over time. This has to do with a relative confidence. I'm interested in assessing the probability or likelihood of observing this particular mean value right now. And the central limit theorem is informing us as to whether or not that observation is in fact likely. If it is, I'll include it in my portfolio. And if it isn't, I will exclude it. The key idea here is, yes, the data generating distribution is certainly going to change over time. But for example, at this particular point in time, our fixed normal distribution by the central limit theorem that we're kind of calibrating to our sample data is doing a reasonable job at proxying for that center. And what I'm suggesting is if the space is reasonably stable and you have some sort of ephemeral probability question, you can answer it by applying the central limit theorem, even though over time that population or data generating distribution for your sample mean is going to change. And that is a very useful concept. Too long didn't watch. Here's your executive summary. Random variables define a set of outcomes with accompanying probabilities or likelihoods, depending on if you're operating with a discrete or continuous random variable. That will dictate whether or not the mass function gives you a probability, or the density function will give you a probability of observing values in a particular region. Anytime we draw a random variable, we are dealing with an empirical distribution, and that is effectively a random variable itself. We don't get the same empirical distribution every time. We create a series of draws, and that distribution generates statistics. If draws are from the same population distribution, i.e. it is time invariant, empirical statistics, subsequent probabilities, and distributions will converge by the law of large numbers. Clearly, this isn't the case in practice, as we are battling data drift, time variance in distributions, and the lack of convergence in subsequent statistics and probabilities. Given draws from a population distribution are in fact random variables, statistics are also random variables, the big question is, what distribution do they follow? The distribution of sample means follows a normal or Gaussian distribution, regardless of the population or data generating distribution. This is quite literally our bridge between theory and practice, statistics and probability. We can unlock an entire suite of tools from confidence intervals to hypothesis testing. If the population or data generating distribution is fixed, then the distribution of sample means will certainly converge to a normal distribution as the sample size becomes arbitrarily large. And probabilities will be precise in the frequentist sense. In reality, population or data generating distributions are not fixed and are time variant, leading us to generate incorrect probabilities and draw statistically incorrect conclusions, just as we saw in the NVIDIA stock return example, where it suggested we had to wait 45,000 years to observe a negative return in a block of 90 days. Though distributions in reality change over time, the central limit theorem can offer a snapshot, which is useful locally for generating probabilities, as we saw in the trading signal example, where the sentiment distribution producing a trading signal or trading decision is likely to be more stable in that short region of time required to generate a decision than it is to be stable over a series of days, which doesn't matter nearly as much because we will continue to resample data and recalibrate our new model. And this is effectively why we all still have jobs. Some future topics, technical videos, and other discussions to look forward to. This idea of advanced Markov chains, something you would see in a class on stochastic processes, non-Markovian models, fractional Brownian motion, Volterra processes. These are some of my favorite mathematical structures. I would love to do a video on these topics. I'm uncertain what the general level of interest would be, but I will probably cave and make videos on these ideas in the near future. I want to talk about deriving the Black-Scholes equation, the PDE, analytical and numerical solutions. We have to get to Kalman filters and non-stationarity. That is effectively what we saw herein with the population or data generating distribution for the sample mean changing over time. There's that time variance, a big problem in quant modeling that I talk about all the time on this channel. I'd like to get into the idea also of risk neutral measures, complete versus incomplete market models, reinforcement learning for delta hedging, and even approximating pricing functionals using neural networks. We're starting to get into more niche topics that really are where my research interests lie. So, depending on what you'd like to see next, let me know in the comments section below. And I haven't forgotten about our quant builds. I have a whole bunch of ideas. This idea of live neural network stochastic volatility model calibration. I'd like to implement the Kalman filter model with regime dynamics. We've already covered Markov chains and hidden Markov models. Once we cover the Kalman filter, we can apply it in some sort of live system. And of course, this idea of an automated delta neutral trading system, which I have been toying with for quite some time. I've been building out the infrastructure, and I think I would like to tackle it maybe this month, but it will largely depend on what you guys would like to see. So please let me know in the comments below. It certainly helps me decide what videos to create next. And that's going to do it for this video on the central limit theorem for quant finance. I hope you enjoyed. I hope you learned something. This video certainly took a lot of effort to create. So if you enjoyed it and you want to see more like it in the future, please like, comment, subscribe, share. Again, it helps me out tremendously. It is always greatly appreciated. I'll leave a link in the description below if you'd like to get started with interactive brokers. They're the only broker I use. I highly recommend their API. It's what I use in all of my quant builds. I'll leave a link in the description to our Discord community if you'd like to connect with me and other quants. If you want to master your quantitative skills, check out quantguild.com. Other than that, thank you so much for watching, and I will see you in the next video.